Welcome to Presentation 17. Today I'm going to be talking about servo motors. I recommend that as a prerequisite you review Presentation 8, 9 and 10, which deal with timers and counters. Now the servo motors belong to our layer 3 in our architectures. Now today's agenda, I'm going to be talking about how servo motor functions and how we have to manipulate our register to generate the correct signal to interface with servo motors. And after that, I'll develop a sample program. So let's start with some definitions. So a servo motor is a type of motor that can move its shaft to a specific position, stop there, and hold that position. It is commonly used in applications like robotics, RC cars, and clones. Servo motors are controlled using pulse width modulations, that's the PWM signals. The width of the pulse determines the position of the servo motor shaft. Pulse frequency required is a 50 Hz, which means that the period of our signals that we put out are going to have to be with a period of 20 milliseconds. Now, the timer that I will be using for this presentation is timer counter 1, which is the 16-bit timer. Now, as I noted, the servo is expected a pulse every 20 milliseconds. That's the 50 Hz. Next, the length of the pulse will determine the angle of the shaft. For example, if we want a position 0, then we need to send a pulse of 1 millisecond duration. So here we have the servo motor to keep this position, then the microcontroller would need to send a pulse of 1 millisecond duration with a period of 20 milliseconds. Next, if we want the microcontroller to go to a position of 90 degrees, the shaft to move to a 90 degree, we should say, then we need to send a pulse of duration 1.5 milliseconds. So basically this would show the signal to move the shaft of the motor from position 0 to position 90. And finally, if we want to move the shaft of the servo motor to the 180 degree position, then we would have to send a 2 millisecond pulse. So again, we would have to send a pulse of 2 milliseconds duration and with a period of 20 milliseconds. Now, what I'm showing you here is applicable to a particular servo motor. But when you buy a servo motor, the specifications associated with that servo motor will tell you how long these pulses have to be, the pulse duration. And you'll see in our example, I'll show a specification which is a little bit different than what I'm showing you here. Now, this is our microcontroller, and as I noted, I'm going to use the timer counter one, which is 16-bit, and we have two ports that we can use to put out our PWM signal. We can use port PV1, which is the OC1A, and physically it's pin 15, or we can use port PB2, which is known as OC1B, which is physically pin 16. So with this controller we can actually control two servo motors. Okay, let's try to understand how we put together, how we generate the signals to control the servo. So here I have an X and Y axis that shows time and shows number of ticks of our 16 megahertz clocks. So the ticks are going to go from between 0 and a max value. And this red light shows how our timer goes from 0 to its max value. And these are the number of ticks to get there. And this max value is going to be the ICR1 register. So this max value, we control it by putting a value on the ICR1 register. And that value, by the way, has to be 20 milliseconds, the equivalent number of ticks for 20 milliseconds, and I'll explain why. So here we have three different our timer. It's series from 0 to max value, resets from 0 to max value, and resets again. So now I have here, I'm drawing another X and Y axis, which is going to show the output coming out of our microcontroller. So how this is going to work. So first, let me show here a point in the line, which is the output compare value. Now what we want is to be able to generate the proper signal. We want the signal to start high at 5 volts. Then when we reach the output compare value, we want it to go to 0. And then we want it to remain 0 until we again get to the maximum value of our counter, at which point we want it to go back to 5 volts to go high. And then when again we reach the output compare, we want it to go low. And then and that's how we generate our signal. Now, there are certain fixed parameters in this signal that we have to maintain. One of them is the 20 milliseconds amplitude, because no matter what servo motor you have, you are required to put out a frequency of 50 Hertz, which means that your signal is going to have to be 20 milliseconds. And now the duration of the signal being high will drive the position of the arm of the motor, servo motor. So if we want a 90 degree, then this signal is going to have to be a 1.5 milliseconds. So basically, the output compare value is going to have to be a 1.5 milliseconds, or actually the equivalent in number of ticks. And if we want a 180 position, we want the arm of the servo motor to move to a 180 position, then we need to generate 2 milliseconds, which means the output compare number of the ticks are going to have to be equivalent to 2 milliseconds. So the position of the servo motor is controlled by the output compare. The period of the signal, which has to be 20 milliseconds, is set up by the value that we put on the IC-R1 register. So we want the signal to go, we want when the signal resets, has to be at the 20 milliseconds, so we get our correct amplitude. So now I need to talk a little bit about some configuration. When we set up our register, we have to use, there is a parameter which is the compare output mode. And the compare output mode has to be a non-inverting mode, which is going to be the 1A1 equal to 1 and 1A0 equal to 0. Now let's see, let me go through some nomenclature so you understand what's been written in the data sheet. So again, he have number of ticks here and time. Now let's draw our other axis, but before we do, we have here the IC-R1 register is the max value. Next, let's draw the output from the microcontroller. And let's see, okay. So we need to start with a signal of 5 volts. Now, if you read the data sheet, the way they say that is they state that set on button. So you need to, the compare output mode has to be set on button, which means when the signal starts at the bottom, has to be set, has to be 5 volts. That's what that means. Next, if you continue to read the data sheet, it says clear on compare. So when you get to this point, the compare value is true, then you want clear on compare, which means that the signal goes to 0. So when we select our compare output mode, we select the non-inverting, which means that's going to be clear on compare and set on button of the signal. So anyhow, I just wanted to show this nomenclature because it's sometimes a little bit confusing. So I put this banner so remind you that what I'm going to talk about, if you don't understand it very well, you need to look at the, you need to review my presentation 8, 9, and 10. So the first line of code says our clock is 16 megahertz. That means 16 billion ticks per second. Now if I convert this to microseconds, then our clock puts out 16,000 ticks per millisecond. Next. The output that we require is 20 milliseconds. So we have 16,000 ticks per millisecond times 20 milliseconds. That means that the 20 milliseconds are represented by 320,000 ticks. Now we know that our 16 bits can only hold a number as large as 65,536. So that means that we need to use a prescaler. So let's calculate our prescaler. So our prescaler would be equal to 320,000 divided by 65,536, which gives you a 4.8. However, there are only a specific numbers that we can use for prescaler, and that's 864, 256, and 1024. So we select the closest, which is the 8 as a prescaler. Next, so we recalculate the output period. So 20 milliseconds using 8 as a prescaler is going to be our 320,000 divided by 8, which gives us 40,000 ticks. So in resume, we need to reset value count at would be 20 milliseconds equivalent ticks, which is 40,000 minus 1. And the reason I have to subtract 1 is because we start counting from 0. And this is with a prescaler of 8. So this information here is going to tell me how to set up the parameters when I start programming on the register. So now let's look at the specification of our servo motor so we can figure out how to drive it. So it says that we need a pulse width range between 500 microseconds and 2500 microseconds. And then it states that the neutral position is 1500 microseconds. So let's figure out how what we need to do to program this. Okay. First, the servo rotation is between 0 and 180 degrees. So I could argue that 0 degrees corresponds to the lowest value, which is 0.05 milliseconds. Now I'm going to convert this value into ticks. So that would be 16,000 ticks, which is the value for 1 millisecond, divided by 2, because we want a half millisecond. And then we're going to divide everything by the scalar, which is 8. And that gives me 1,000 ticks. So it means that if I want to drive this servo motor arm to the position 0, then I have to put in a value of 1,000 ticks. Next. Now, if I want to drive my motor to the 180 degree position, then I need to send a signal duration of 2.5 milliseconds. Now I need to convert this to ticks. So 16,000 ticks is 1 millisecond. I need 2.5 milliseconds. So I multiply it by 2.5 and then I divide it by the 8, which is my scalar. So I have 5,000 ticks. So if I want to move my servo between 0 and 180 degrees, then I need to send between 1,000 and 5,000 ticks. So now let's calculate the value for the number of ticks for 1 degree of rotation. So I have ticks for 1 degree rotation is, I need to figure out all the ticks that cover between 0 and 180, which would be 4,000, and then I have to divide it by 180. So now, if I want to calculate the number of ticks for any angle, then I do it as follows. So I start with 1,000. If the angle is 0, that means I want to go to a 0 position, then it's 1,000. And then I add the I add the multiplication of the angles times how many ticks per angle. And that's going to give me the number of ticks for any desired angle. Okay, let's talk about our sample program. So number one, drive the servo motor back and forth between 0 and 100. So we have our servo motor here hooked up to PB1, which the name is OC1A. And what I want to do, the first requirement is to drive it from 0 all the way to 80 back and forth. These are. Next requirement, increment the servo motor position by 45 degrees each time. So I need to go from 0 to 45 to 90, 135 and 180. Now 3, wait 1 second before changing from one position to another. Okay, starting 0, wait 1 second, go to 45, wait 1 second, go to 90, wait 1 second, go to 135, and finally wait 1 second and go to 180. Okay, so let's look at the sample code, the program, source code. I will first give you a global view of this program. So we have the init PWM routine, which is the one that initializes the pulse width functionality. Next, we have a routine called the servo motor angle, which has as an input an angle. And what it does is moves the servo motor arm to that particular angle. And finally, we have the main program, which initializes whatever needs to be initialized. And then it calls the servo motor angle to place the servo motor arm as required. So let's get into the details. So let's start with the init PWM routine. This routine is going to set the output for the pulse width modulation to pin B1, where you can see it here. This is pin B1, and the name of this is called the OC1A. So that's what these 3 lines of code are doing. Next, these following 3 lines of code, what they do is they set the pulse width modulation mode to fast PWM, and also sets all the parameters needed to get the correct pulse, which I already explained previously. Next, I'm showing here the calculations, which again I've already showed how to do this. And then we have these 3 lines of code, which what they do is they select the prescaler to 8. Finally, we have a parameter, the ICR1, which defines the period, which corresponds to a 50 Hertz signal. And we give the ICR1 the value of 39,999. We don't do 40,000 ticks because we start counting from 0. Next, we have the servo motor angle routine. This routine, it has as an input an angle. So what this routine does is going to calculate the number of ticks required to place the servo motor at the particular input angle. So that's what this calculation does, which I already explained. And then the final line of code is going to take the OCRA register, and it's going to load the value which I call rotation, which is the number of ticks to place the servo motor angle at the desired angle. The servo motor arm at the desired angle. So let's go to the main. In the main, we're going to initialize the PWM, and then we're going to get into our infinite while loop. So this statement is going to set the angle of the arm, of the servo motor arm, to 0. Next, I'm setting it to 45, setting it to 90, setting it to 135, setting up to 180, and then I go back to 0 and do that forever. And that's what was required. So I hope I've given you a good explanation of what this routine is doing. Okay, so we finally got to the summary. So today I talked about servo motors. I provided definitions and a sample program. So I hope you've enjoyed this presentation, and thank you very much for taking the time to spend it with me. Thank you. Bye.